So it's a capital P, so what is it?
Power
It's the power,
is equal to change in energy over time, change in time.
okay? So it's, power is a measurement of how the energy is changing, right? Now, whether that's like a change in kinetic energy, or a change in gravitational energy, or in elastic energy, we don't really know, but, yeah.
So does that mean if you have the work, you can get the power through the antiderivative?
Yeah, let's pause for a second. So we get this in watts, okay? We get this in watts. Is that cool? And then this is oftentimes, we're gonna call this the work, right? And if your force is constant, okay? If your force is constant, then we can say like the work is the force that you applied times the distance that you moved while it was being applied, right? If I go back to this, if my force were constant, what would this look like? What's the area of that rectangle? It's just fx, right? Does that make sense? So, and this is over the t, but what is the change in position over the change in time? That's the velocity, right? So one of our power concepts is just Fv, right? So you will see a question like this. It says, here's your object. The power is this, the velocity is this, how much force was being applied? They just want to know if you know this equation, right?
Yeah.
There's no deep understanding here.
Oh, yeah, that's the next one.
Oh, is it on there? Well, there you go, now you know where it comes from. A couple things about this, though, is that, and this is important, I don't want to gloss over this, okay? Force is a vector.
Yeah.
This displacement is also a vector, right? And if you look over here, force and velocity are both vectors, true?
Yeah.
So how do you actually calculate the work?
What do we do with, I don't know, I was gonna say like cross product.
Dot product.
No, it's a dot product.
Yeah, dot product.
You need to understand that the work is actually a dot product. If you're pulling it in the direction that it's moving, that's cool. Then you just do F times X or F times D or whatever. But if you're pulling it at some angle here, right, then the work you're putting in is equal to F dot D, which is FD times the cosine of the angle between them. Right? Same thing over here. If your force is in this direction, but your velocity is in this direction, you'd have to use some sort of FV cosine theta. But it has that on there. There's a reference there. It says, look, you see the giant dot in the integral,
Yeah.
right? That giant dot is saying, don't forget you need to use the dot product because they're not in the same direction. And then the next one says, I wrote it as delta E. I wrote it as delta E. What was your question? Luke, you asked me a question. What was it? You said, can I do the antiderivative to get something?
I can't remember. Oh,
So-
I was talking about work,
Oh,
just getting work from the power.
So this is, on the sheet it says dE dt, right?
Yeah.
Okay, right, yeah.
So this means that if you had, let's say, an equation for the energy, right, you could figure out the power if you need to take an antiderivative. I've literally never seen that, okay? But you understand that this also just means the change, so I'm happy with that. You could take the antiderivative of both sides, right? to solve for the work, like if you rearrange this, if you did power times the time is equal to the, right? If you took the antiderivative of both sides, this side would just be equal to the work done. Again, never seen it, but mathematically it makes sense. You guys look tired today, you alright?
It's one of those days, man.
Is it?
It is, man.
How's your couch?
This couch that Mrs. Pata bought is ridiculous. Like, the ottoman for the couch takes up half the room. I don't understand what we're doing with this thing.
Everyone can put their legs
Well,
on
it's
it.
actually.
Yeah, actually.
A good couch really makes the house.
If everyone's on the couch, you can just lay down on the ottoman.
Really, it is, we have plenty of room. My youngest doesn't even have to touch the floor anymore. Like, she just bounces from couch to ottoman to couch to a new room.
That's hilarious.
What's the next one?
Something.
You changing UG.
Oh, yeah, so, if you want to solve for the gravitational potential energy, what do you need to know?
Sorry, do you mind just going down really quick to the work equals force times distance one, the one you were, I just wanted to. Alright, we're good. Alright, I got it, I'm good now.
You got, you sure?
I'm
There.
sure we're good.
Oh, there's.
Yeah.
Archie, no one asked.
So, if you want to change the gravitational potential energy of an object, you have to change its height.
Yeah.
Oftentimes, we just say MGH, we're implying that wherever it started was the zero height. Does that make sense? So we just go like that. But that's, this, I don't know. If you don't understand this, I can't help you tonight. I don't want to be a jerk about it, but.
Wait, what, if we don't understand what?
Just that equation.
Oh, yeah,
Yeah,
yeah.
actually.
Like,
That's probably the most simple one.
But-
Besides like F equals M, right?
right, I mean, these should be like, you look at it and go, yeah, I got that, we've used that before, I'm good. Let's borrow that last, okay.
I don't know what's so wrong with it.
The next one's interesting, let's take a moment, I'm even gonna add a new, So, let's take the bicycle tire as our example again, okay? Let's take the bicycle tire, let me draw it, hold on.
Oh, come on, thanks.
Really, it's just.
Beautiful. No. Maybe no.
So, let's talk about an ant riding on a bicycle tire, okay? The ant is on the tire and the ant is here, right? Now think about it, if the tire is spinning, right? If the tire is spinning, the ant's gonna have to hold on pretty tightly. Does that make some sense? But ants probably have some stickiness on their feet, or they're using some sort of something to hold on, because you've seen them walking on the ceiling, right?
Yeah, it's pretty much so good.
Right? So here's our ant. Our bicycle tire is going around this direction.
What?
Is that cool?
I'm just stupid.
So, a couple things are happening. One, is our ant moving? I would say yes. But our ant has two kinds of motion, doesn't it? Right? What's one kind of motion?
Sure.
Tangential,
That's right, so it has some tangential velocity. Right?
which is straight line, right?
Yes. It's tangent to the circle, it's going in this
That'd be
direction.
F equals MA, all that stuff.
Maybe, but I mean, just it's going in, it's velocity, it's going in a straight direction. But the whole thing is rotating, isn't it? So what do we call that?
Angular.
We call that the angular velocity. Is there a relationship between those two?
Of course.
Yes, there is, and you need to know this. This is fundamental, and I don't know that it occurs on here. Let me check. Oh, it is. There it is.
Yeah.
Yeah, so this is fundamental, and you need to like circle this one and write this one down, because this is fundamental. Okay? It says, if you want to calculate your linear velocity, you need to know your angular velocity and the radius. Now, and you have a good understanding of this, like, if you're the ant and you're going around, if you're closer to the inside, you're technically going slower in this forward direction. right? It's like being on a merry-go-round. The closer you are to the center, the actual slower you're going, right? So that's what this says.
That's
It
why if you
says,
hang on the outside, you really feel it.
yes, you can, and you're going much faster.
And why people want the outside cars are rolling street, because.
Exactly, like there's a much better ride on the outside. Now, this is okay to me, true? So if our ant, let's say it's on a bicycle tire and it's slowing down as it goes. It's slowing down as it goes. So over time, as it comes back to here, maybe this velocity is a little bit less. If your linear velocity is less, would you say you were accelerating?
Yeah.
I would say I was accelerating. In fact, if I had to think about it in this context here, if it's slowing down in the linear direction, what direction is the acceleration?
Opposite direction.
It's opposite, true? Does that make sense?
That's centrifugal acceleration.
It's what? No. It is not.
That would be.
That is linear acceleration.
Are you going to draw
That
the
is just
centripetal
I'm
acceleration?
looking at something
Linear
else.
acceleration.
Ignore me. Just ignore me.
Linear
The
acceleration.
acceleration would be
But here's the
slowing
thing.
down.
If you have linear acceleration, what does that mean about the rate of spinning? It's also getting less, which means you have then, this is the same relationship between your linear acceleration and your angular acceleration. You see, these are the same thing though, because if you just divide both sides by t, v over t is a, and omega over t is alpha, right? See how that works? You okay with that? But here's the thing. Is our ant going in a circle?
Yeah.
Well,
Right?
Relative, not relative to it.
It may not know, right? But relative to the wheel, is our ant going in a
Yes, it
circle?
is going in a circle.
So, if you need to go in a circle, doesn't there have to be an unbalanced force on you?
Yes,
Which way?
towards the center or wherever you're standing.
Inward toward the center. What's that?
Centripetal force.
That's our centripetal acceleration,
That's what I meant.
right? This is our centripetal acceleration here. So we have two different names for these. This is your centripetal acceleration, AC. But our ant is also slowing down, so we call this one our tangential acceleration, AT. And I haven't seen it in a couple years. But you could get a problem like this. It says, in what direction is the acceleration, or what is the value of the acceleration of the object? But here's the thing.
Oh, yeah.
It's accelerating inward, and in this, also backward. So if you want to solve for the overall acceleration,
Yeah, the vector.
you have to add the two vectors. So this would be your overall acceleration. See how sneaky that is? If you're an object going in a circle, if you're slowing down, you have tangential acceleration, but if you're going in a circle, you also have centripetal acceleration. That's like a kick in the teeth
Why
right
is he
there.
slowing down? Like, why does he have a tangential? Or we're just
Well,
saying?
if it's the bicycle tire and you spin it, it's gonna slow down over time,
Okay. Oh.
right?
Air
Just because
resistance,
the
all that stuff.
air resistance, the friction with the axle on the hub, right?
What did the ant get sloshed?
Well, it's, someone's holding it, right?
Okay.
Now,
imagine it's that.
let's do the acceleration. What's the centripetal acceleration?
MV squared. It's
So,
just V squared, 'cause
The acceleration is just v squared. If you want the force, it's mv squared. Is that cool? But look over here. Don't I have an expression for v?
Yeah.
If I substitute this v into here, I'm gonna get omega r all squared divided by r.
Which is just, oh my god.
And now I have omega squared r. See that? Is that on your sheet?
Yeah, but-
Probably.
It probably is.
It is.
Can you see it?
It is.
So if they give us our angular speed of
Searching. Yeah, MG is fine.
Oh, it's above it, it's right below it.
Okay.
NG, or UG.
I've not heard about it, just using my computer. I'm looking at the reverse, so.
Where's that equation?
It's right below delta UG.
Oh,
Man, I'm going in order.
oh,
Yeah, I
yeah.
realize you are
It's-
going over.
It just.
I didn't realize,
It's
yeah.
like equal.
So we're supposed to curveball going down to V equals R, oh my god.
Oh, I did. I didn't actually know that was on there. I mean, of course I knew it was on there,
Yeah.
but I didn't.
You're just going the long way around.
Let's take a quick brain break. It's been an hour.
And I wanna go watch